So this talk will be about locality and freedom of choice. I hope it won't be very controversial, so I'll stick to the usual phrasing of both concepts. And here in this imagery here, this picture, you can see, two figures, the scenario that we all love and know. So here is Alice, here is Bob. Both of them are performing some dance. And you can see they're attached to some strings of zeros and ones, which are in causal terms. So there is some cause affecting Bob when Alice is performing her measurement. As for the freedom of choice or lack of freedom of choice, I think of someone pulling the strings. So if you can follow with this kind of imagination with me, please. All right. Okay, so here's my second slide. So basically, this talk will be a story which was told in this paper here, which was just recently published in PNAS 2 weeks ago. In this company here, so it is co-authored with Emmanuel Potters, James Yearsley from London, Christoph Gallus from Gießen, Germany, and Eva from Krakow. So I tried to give you to walk you through this paper in a gentle way, so that you can perhaps look afterwards what is there, how do proofs look like, and what is the mathematics inside. So I have two goals for today, which first comes to the question, okay, so which is more costly, locality or free choice? If I ask such a question, it means that I should somehow, okay, first, so the first impression is that both those two concepts are totally different. So they certainly have different ontological connotations. So how to compare those two? So I'll need to give you some measure of those two. And if I would like to compare them, this measure will have to be built on the same concept in order to make a comparison. Then I will show how to compare those measures, and both from the theory and beyond, in more general scenarios. But before that, I'll need to retell a story about Bell experiment in my way. So far we have heard quite a lot about it in terms of joint probability distributions. So in this talk, I will focus on conditional probability distributions, which is totally equivalent. I think it's more general, though, which will allow me to treat freedom of choice as well, not only locality. So as usual in the both scenarios, so we have two parties. Here's Alice, here's Bob. Alice chooses measurements, Bob chooses measurements, X and Y, both obtain some outcomes. So they repeat those experiments many times for different choices, and they collect statistics. This statistics will be called experimental behaviors. So it is here. So it's the probability of obtaining outcomes A, B, given a choice of settings X, Y. There's also another component into the story because I'll be speaking about free choice. So there's also a probability distribution, so distribution of settings which they choose. So the story goes then as follows. Then we would like to model those behavior in some way. So we postulate there is some hidden variable with some distribution, which should, in a probabilistic way, the usual probabilistic way, recover those results. So this behavior and this distribution of settings, and postulating or giving a hidden variable model simply means that I need to give those three components, that is this probability distribution, as well as the distribution of the lambdas. So far I haven't assumed anything about the causal structure. Then the causal structures comes in, and there is this, you may postulate there is this locality assumption, which boils down to this factorization condition, and the free choice assumption, which is here, that is lambdas do not depend on xy's, either in this way or you can rewrite it in that way. whatever you wish. And then perhaps in order to be fair, I need to add another assumptions, which is arrow of time. And that is, there's no backward times causation. Then you obtain this causal diagram, which is here, which we all know. And with all those three assumptions, you can derive value inequalities, and you can prove that those assumptions have certain testable constraints on correlations, and we know that quantum theory doesn't violate them. That means that some of our assumptions are not true. So today I will take arrow of time for granted, and I'll just focus on locality and free choice. So what does it mean that locality is violated? So in the causal language, that would mean that there is an arrow from Alice's side to Bob's side. Well, either it is from X to B or A to B. One might call it parameter dependence or outcome dependence. So both these two arrows combine into the factorization condition. If this factorization condition doesn't hold, that means we have this equation. So there's no equality here. Locality is violated. As for the violation of freedom of choice, there are two arrows which go from lambda to X and Y, and this allows me to violate this condition. That means freedom of choice. So that is a violation of locality, freedom of choice. Sometimes, at least sometimes, those conditions have to be violated. Well, at least sometimes. So here comes a heuristic idea how to compare those two on an equal footing. We can simply ask the question, how often, given assumption, whether it's locality or freedom of choice, can be retained while safeguarding the other assumption. So here, we don't have, so here, for example, if I violate locality, so I assume that I would have freedom of choice here, so no arrows from lambda to axis, but I will allow sometimes to appear, for this arrow to appear. For freedom of choice, I will assume that there is full locality, but I will have to allow violation of free choice, which means those arrows. So here's the heuristic idea, how to put it in mathematical terms. So suppose that I have a hidden variable model which violates locality here on the left. This one violates freedom of choice on the right. Then I can split the underlying hidden variable space lambda into two subsets. On the first one, on the local one, locality will hold, while on this non-local part here, I will assume that so this set is defined in a way that this condition doesn't hold, at least for some x and y. And the same for the freedom of choice. So lambda NF, there is no free choice, means that for those trials, for those lambdas, this condition fails, at least for some x's and y's. Once I have those subsets defined, I can ask how often it happens. So, well, it happens for those for this particular model, which I'm considering here on this part of the hidden variable space. So, how often does it happen? I simply need to integrate or sum over the subset. So, this tells me how often Alice and Bob retains locality. While here it means, so this expression says, okay, so in those cases, in this fraction of trials, freedom of choice is retained. All the stories is, of course, told for a very particular model which I'm considering in this particular case. But let's get rid of these particularities and consider arbitrary model. This allows me to define a measure of locality and free choice for a given behavior. without reference to any underlying specific model. So how to measure locality? So measure of locality will be a maximal fraction of trials in which Alice and Bob can be local, so it means they do not need to communicate, trying to simulate this particular behavior for any distribution of setting which they can think of, optimize over all possible strategies with freedom of choice. And similarly, for freedom of choice, I will define measure of free choice as the maximal fraction of trials in which both of them can be free, trying to simulate given behavior that I'm asking measure of locality, measure of freedom of choice for any distributional settings, optimize over all conceivable local strategies. So how to put it into mathematics? So here is precise mathematical formulation of those measures. So measure of locality is simply a maximum is the maximum over all possible models with freedom of choice. Here I sum over this local part only here, and of course minimize for any choice of settings. And similarly for measure of freedom of choice, of free choice. So measure of free choice is a maximum over all possible local hidden variable models, where this quantity tells me how often freedom of choice is retained. And again, I have to minimize over all possible distribution settings. This will be important in a moment. So I just emphasize that those measures give me the fraction of trials in which I need to retain a certain property, locality, or freedom of choice in order to simulate any possible distribution of settings. That is this minimum, which why is present here. Note that those measures are based on the same concept, exactly the same context. It's a fraction context. You might, if you're familiar with local fraction or local content, this is this measure of locality. This is exactly analogous one for freedom of choice. Then here comes the first result, which is as follows. You can prove, and that's what we've actually proved, that both those measures are equal. They have to be equal for a given behavior, whatever the distribution of settings. Before I give you a sketch of proof and why it's not that, I'll try to convince you why that is not so trivial. I will just mention that this theorem holds for any number of settings and outcomes, and any scenario with arbitrary number of parties. So this proof can be generalized. So here you have measure of locality, measure of free choice, and you may ask, okay, so why is that so striking? After all, we proved that both measures are equal. So perhaps it's just possible just to replace those arrows. So supposedly I have this kind of scenario here, and in some trials on some part of the hidden variable space, I have these arrows, so perhaps I can just switch those arrows, and that will do. Well, it won't, and I'll try to convince you why. So here's sketch of proof. So supposedly that in order to prove it, first I need to get rid of those minimas, which are here. And I'll tell you why it's not so easy. So supposedly that I have this this behavior and this distribution of settings modeled through some hidden variable model. So that means that I have those three quantities, that is this one, and this one. They're fixed. And supposedly I wanted to retain those two in order to have proper simulation of the behavior. But I wanted to change this distribution of settings in order to somehow get rid of those minimas. So what would we do? So the easiest way would be, okay, so let's retain those two so that we have proper modeling of this part. And replace this quantity with something else, which will give me another distribution of settings. And in this way, I will get rid of this minimum here. It might do, but it has to be consistent. This quantity here has to be consistent with those choices here. And they have to obey this equation, which is the usual bias rule. That is, this quantity is given by this new distribution of settings, which I want to simulate. But note that there is this P of lambda xy, which is taken from here, as well as P lambda. So as long as you have freedom of choice, there's no problem because those two cancel out here and here, right? So this is properly defined, and you can proceed in that way. So it's really trivial to get rid of this minimum here, and that's why people are considering local fraction. They simply omit it because it's always satisfied. But note that for freedom of choice, it's not. It doesn't suffice because those two terms don't cancel out. That means that this quantity could be greater than 1. So it's not so easy to simulate starting from some model from a hidden variable model for behavior and distribution of setting, to switch it to a different distribution of settings. And in order to do this, you have to construct a new model with the same property, which conserves given degree of locality or freedom of choice in this more harder case. So this can be done. You can get rid actually of both minimas. This is trivial, so this is rather hard, but you can do this. So you can get rid of the minimas, and then you can provide a bijective construction showing that those two measures are equal. So this is the first result. So switching between locality and free choice buys us nothing in terms of modeling. It's equally hard to model given behavior with local models and models with freedom of choice. So that's the first part. So again, it's a restatement what actually of the first theorem. So both measures are exactly the same. You have to violate locality or violate freedom of choice, or equally frequently if you want to model given behavior, right? It goes more or less along those lines which are here. So I would rather discover one true cause than get a king of Persia. So we know that inferring causal relations is rather hard. Apparently nature doesn't favor one solution. So the mathematics says that it's equally costly. Right, okay, so it's a structural theorem which has been proved. And then you might ask, can we actually measure it? Because what we measure is a given behavior. So can we say what is actually the number here? What is the figure here? In order so to know, okay, so how local or how non-free or how free a given behavior is. And this brings me to the second part, how to calculate those figures. But before that, I'll need to finish the story with Bell's theorem. So let's assume that we have this binary setting scenario with two possible outcomes. We all know that then you create those three expressions, which are important in this case. And then Bell's theorem says that realism, locality, and freedom of choice, perhaps no retrocausality as well, require that those expressions are less or equal to 2. This is this local bound. In quantum theory, we know that zero-sum bound says, okay, so it can go up to 2 square root 2, which is not as high as 4, which is attained by PR boxes. Then this scenario was, very, very well researched, and quite a lot of, well, perhaps everything is known in this case. So a very important result is this result. How does non-signaling polytope looks like? So here are these non-signaling conditions. So we know that these non-signaling polytopes, which assumes, by the way, freedom of choice, because, well, in that framework, it's all when people research this area, they always assume freedom of choice. So this non-signaling polytope is spanned by PR boxes, 8 PR boxes, and 16 local strategies, and we know that this local area here, red, is given by those equations, those 8 equations, and that is known. We can use it to calculate our quantity, which is measure of locality or freedom of choice, and the result is that measure of locality for non-signaling behavior, still not quantum, but more general, for non-signaling behavior with binary setting, is equal to this quantity. So you're all familiar with this. So if you write an axis with possible values for S, so this maximum value of S above 2 gives me exactly a measure of locality of free choice. So it gives you, well, basically, it gives you an interpretation of the amount of violation of CHSH inequalities. So the answer is, what is the interpretation? The interpretation is, well, it is the maximal fraction of trials in which you can be local and free in order to simulate this scenario. So how to prove it? So the proof goes along the lines which I think they can be guessed from those works. So this, though perhaps most of us are familiar with this Abramsky, Ruiz and Shane's work about contextual fraction, which is a more general notion that for this local scenario, it boils down to the local fraction, which was researched much earlier because it comes from Alicia and Weinman, and then you can also find those results about complex compositions in this work, which relates to this, which relates to this scenario. So how does it work? So you use this convex decomposition of a given behavior, and you can easily justify that this mu L. So it's easier to work with mu L since mu F is, well, less research. We know more results about locality, assuming free choice. Actually, nothing we know about violation of freedom of choice. So, but owing to this result, we can back up on those results, and you can use this convex decomposition. You can prove the upper bounds, and then knowing how this upper bound, and then you can prove that this bound is saturated. Knowing from the knowledge, how does this convex polytope look like? So this, so find to find this probability distribution in this coefficient in this convex decomposition. So this is still quite general. So nothing about quantum theory. So now let me proceed. It's my penultimate slide to quantum statistics. So how does it look in the quantum case, very particle case of the quantum statistics that we know how to get from the Hilbert spaces and so on. So we know that for a binary setting scenario, there is this zero-sum bound, which says that for ballast states we can be free up to this amount. In this fraction of trials, then there is this beautiful result, which goes to Alizur, Popescu, and Rollish. So they considered a scenario with arbitrary number of settings, with two parties for a balanced state, you can show that this local fraction and the free fraction goes to zero. How do they get it? They get it through the use of chain bound inequalities, and in this case, you don't have to bother with saturation because saturation of the bound, because it goes to zero. And finally, there is this beautiful result. It's a real nugget, I think. How do these measures actually perform for arbitrary two-qubit state? For arbitrary two-qubit state, which can be written in that form in Schmidt decomposition, for arbitrary number of settings. And they proved in this work with Portman, Branciard, and Chisson that this local fraction, because they proved for local fraction, is equal to cosine theta, where theta is given here. So so due to the fact that both measures are actually equal, so it also gives you exact values for the free choice. Okay, so this brings me to the end. So I'm just wrapping up, and so what I've given you. So I've given you, I've defined it for you two measures. So local fraction and free fraction. So local fraction was well researched. All these results are known. But in this work, which we did, so we have defined exactly the same measure for freedom of choice, retaining locality at full, and we proved this general result, general theorem, structural theorem. Then this gives the interpretation to the amount of violation to the CHS inequalities, which everybody always give in all experiments. And unfortunately, if you allow an infinite number of settings for maximally entangled states, those measures go to zero. That means that on each trial, if you want to be free, on each trial there needs to be a connection between Alice and Bob, some causal connection. Or if you want to retain locality, on each trial, those settings has to be set. I'm not saying that this dependence has to be deterministic. I'm just asking the question, or answering the question, how often some causal influence has to be imposed on Alice and Bob. It could be a probabilistic one as well. Nothing about determinism was assumed here. And you can also provide those measures for two-qubit states for any number of settings. And this brings me to the end. It's 30 minutes almost. And thank you very much.
What bothers me about your talk is that it seems to be based on assuming the microscopic world is governed by classical physics, that is, Bell's classical hidden variables. And you expect different things. Have you tried to analyze it, assuming the microscopic world is governed by Hilbert space quantum mechanics, which, you know, has been involved for something under 100 years, but for a long time?
Well, yeah, you're perfectly right. So the story here, and I think is that, well, okay, so we are assuming, you know, the usual causal framework. I would say, okay, which comes from Bell, now well, you know, formalized in present time by Judah Pearl, and we're trying to simulate those relations with certain causal relations. And well, that is the story. So I'm not considering here there's, you know, quantum causes or something like this, because I think that, well, at least this shows that you can always simulate a quantum behavior if you have non-locality, right? And the question is, okay, so how non-local the world has to be, would have to be in order to simulate to what extent it is non-local, or maybe to what extent our settings are rigged. Yeah, that's exactly the story.
But it seems to me that in Hilbert space quantum mechanics, our world is local. There are no non-local influences. And I know of no reason to deny free choice in the usual sense. So isn't your result simply based on the assumption of classical physics at the microscopic scale?
It is based on the usual classic approach to causality, I would say, without postulating any special mechanisms, because always you have to come up with a model which simulates given behavior. So, like for example, in case of if we know that we can simulate maximally entangled states for Alice and Bob with just by sending just one bit of information into the Bacon model. They can be artificial, but they're classical. Yes, you can always do this, but you have to allow yourself some non-locality. And I don't believe that Hilbert mechanics is local. I don't know. Okay, maybe it's local, but in some other sense, not in this sense. I think that was proved by Bell.